lectures of algebraic quantum field theory. And we have the pleasure to welcome Professor Valter Moretti from the University of Trento, who will speak of quantum field theory in space-time with null-like boundaries and the bulk-to-boundary correspondence.
Thank you. First of all, let me say that it's a true honor for me to be here to give a seminar on this occasion. And I would add that I joined this community several years ago, but I feel myself still as an outsider in some sense. I don't know why. Okay. My seminar concerns some recent results obtained in collaboration with my colleague Claudio D'Appiaggi and Nicola Pinamonti from Hamburg, and concerning the last paper, which is still work in progress, in collaboration with Romeo Brunetti of Trento, my university. That is the plane of the seminar, and let's pass directly to the general motivations and the general results. Okay, the motivation, the general motivation of these all these papers is to study how the asymptotic, in general asymptotic, but not necessarily asymptotic, geometry of certain classes of spacetimes selects distinguished Hadamard state for linear quantum field theory, and to investigate the general properties of those states. I have to say that for the moment all the theory is confined to the case of a free field. Linear means free in that case. Free, obviously, it interacts with gravity. We hope after the summer to pass to consider the case of interacting fields with self-interaction. The general structure of all considered class of spacetimes is the following. We have a bulk, a spacetime which will be in all cases globally hyperbolic, and we have a boundary. In general, this is only a part of the boundary, but during this talk I will call it the boundary. This boundary is actually a light-like three-dimensional submanifold of the spacetime or in certain cases of a larger spacetime when one deals with spacetimes which are asymptotically flat at null infinity. In this case, the boundary doesn't belong to the manifold, but is a boundary in a larger unphysical manifold. And this picture represents a conformal diagram. The future null-like infinity is obtained approaching the infinity along null-like geodesics. The first case we shall examine is this one, the class of asymptotically flat spacetimes and at null infinity. A second class we shall examine is a class of expanding universes with the cosmological past horizon. The third, actually this is only one manifold and not a class. The third case is part of the extended Schwarzschild spacetime, this region containing the Schwarzschild wedge, the event horizon, and the black hole region. And the last case we consider is nothing but a diamond in the four-dimensional Minkowski spacetime. The boundary in all those cases has a suitable structure, which is made as follows. The boundary is diffeomorphic to this product, or is a union of several pieces of this form, and the metric on each part of the boundary takes this form, where this is the standard metric of a two-sphere, and this one is the metric in light coordinates in the two-dimensional Minkowski spacetime. So we admit that there is a coordinate patch around the boundary where the metric takes this form, and the boundary is reached when v equals 0. U is an affine parameter of the null geodesics forming the manifold, the boundary. Okay, in all examined cases, actually in the first two cases, in the class of asymptotically flat spacetimes and in the class of cosmological models, the boundary admits also a certain group of diffeomorphisms, which has a certain meaning I will analyze later. And it's possible to equip the group with a suitable structure in order to obtain an infinite dimensional Lie group. And in general, depending on the case, the action of the group on the boundary takes this form. G is a generic element of the group. This is a function depending on the element, and those are functions depending on the element of the group. It happens in all examined case that the group G includes a suitable group of Killing isometries of every bulk which matches the boundary. Namely, there is an injective group of homomorphisms which transforms each element of a certain group of isometries of the bulk into a corresponding element of the group of the boundary. In this case, in the case of asymptotically flat spacetimes, this group is the full group of all Killing isometries of the space M. It's important to stress here that the boundary structure is universal, namely the geometry on the boundary doesn't depend on the bulk. The metric takes this form, and the group of diffeomorphisms, this distinguished group of diffeomorphisms, doesn't depend on the bulk, but only on the structure of the boundary. Okay.
The image of this embedded group GM.
Pardon?
The image of the embedded
yes.
group GM. That depends really on that.
Yes, obviously, yes, because these homomorphisms depends on them. So also the image. Okay, yes, and obviously the image is finite dimensional. Okay, as we have no, it's possible to construct with this geometry a symplectic space on the boundary. So we have a space of functions, and in all considered case, the space of function we deal with is contains always the space of compactly supported smooth function defined on the boundary, and we define also this symplectic form on this space. The coordinate u is that which appear here. Actually, it's possible to rescale the coordinate u without changing the symplectic form. Since we have a symplectic space, the space is the precise shape of this space is fixed once one has a particular class of spacetimes. In general, is different for asymptotically flat spacetimes or cosmological expanding universes, but the space doesn't depend on the bulk. Okay, is a universal as the geometric structure of the boundary. Okay, since we have a symplectic space, we also have a sister algebra which is associated in a standard way and defined up to star isomorphisms to this symplectic space. It happens in all considered case that the structure appearing here is invariant under the action of the group of the boundary. As a consequence, it's possible to define a representation of the group in terms of star automorphisms of the Weil algebra of the boundary. Okay, but this is completely unrelated with the bulk, and now we are interested in studying the interplay of this algebra of the boundary and some algebra, for instance, of field observables defined in any different bulk which matches the boundary. A natural candidate for the algebra in the bulk is the Weil algebra generated by a scalar field, a Klein-Gordon scalar field. Okay. And in this case, the Weil algebra is obtained constructing a symplectic space where the space of functions is the space of solution of Klein-Gordon equation, which have compact supported data on Cauchy surfaces of the spacetime. I always consider globally hyperbolic spacetimes, and the symplectic form takes this standard form. The relationship between the algebra of the bulk and that of the boundary is obtained, is sketched in this image, this figure, is obtained by extending the solution associated with some Cauchy data up to the boundary and taking a restriction of the solution. In case of an asymptotically flat spacetime at null infinity, it is necessary to rescale the field before taking the restriction, because at infinity the field vanishes. So we have to use an infinite rescaling. Okay, essentially by the Stokes-Poincare theorem, without paying much attention to mathematical details, using this form, I don't know, this one, this form of the symplectic form of the boundary and the other form of the symplectic form in the bulk, it arises that the restriction, the map which associated a function, a wave function in the bulk with its restriction on the boundary, preserves the symplectic form. Actually, this is not straightforward, because information may escape by this apparent point. Actually, this is not a point in the manifold in general. it could be a whole. So this identity has to be examined case by case, considering the different classes of spacetimes. Okay, anyway, if the map constructed, as I said previously, essentially taking the restriction of the solutions on the boundary, exists and preserves the symplectic form, then it induces an injective star algebra homomorphisms which maps the algebra of the bulk into the algebra of the boundary. And these injective star homomorphisms is completely determined by this constraint. This object is the generic generator of the Weil algebra of the bulk. Okay. In this way, if you have a state defined on the algebra in the boundary using the pullback of this immersion, we obtain an induced state in the bulk. Okay. Now, it would be nice fixing a state, a universal state on the boundary, which by construction doesn't depend on the particular bulk attached to the boundary, which fulfills the following requirements. No, such that the induced state in each bulk satisfies the following constraints. We may ask that the state induced in the bulk is invariant under all the Killing symmetries, if any, obviously, of the bulk. We may ask for obtaining a state induced in the bulk which has positive energy with respect to every globally time-like Killing symmetry of every bulk. We may ask, very important this point, that the state induced in the bulk is Hadamard. And a natural final requirement is that the state induced in the bulk coincides with known states when the bulk is a well-known bulk. For instance, in case M is the Minkowski spacetime, we expect that the induced state is the Minkowski vacuum. In case the bulk is the Sitter spacetime or part of the Sitter spacetime, we expect, we want actually, that the induced state is the Bunch-Davis vacuum. In case the bulk is the extended Schwarzschild manifold containing the event horizon and the black hole region and the Schwarzschild wedge, a natural candidate for the induced bulk, state in bulk, is the Unruh state, for several physical reasons. Concerning the condition 1, it is satisfied if the embedding of algebras and the homomorphism which maps the isometries of the bulk into the symmetries of the boundary, roughly speaking, commute. In this case, following this chain of equalities, one obtains that the state defined induced in the bulk is invariant under the group GM of isometries of the bulk itself. Okay, so a central question is to determine G-invariant state defined on the bulk. There is a natural candidate which arises several times in the literature, for instance by Sewell, by Dimmock and Kay, but also by Kay Wold in their celebrated report about the uniqueness of Hadamard states in a manifold containing a Killing horizon. bifurcating horizon, and a natural candidate for the G-invariant state on the boundary is that having this two-point function. Obviously, it's necessary to extend this two-point function to the whole symplectic space, because in general this two-point function is defined only in general, but it can be extended. Is defined only on the smooth, compactly supported functions defined in the bulk. Okay. In all considered cases, it turns out that this state is well defined and is invariant under the group of symmetries of the boundary. It arises that this state admits positive energy with respect to the symmetries in the boundary, which arise from time-like killing vector of any bulk spacetime. It also happens that this positive energy property determines completely this state, which must have this form. The proof is based on in the class of quasi-free state. This uniqueness holds. This uniqueness property holds in the class of quasi-free states defined on the Weil algebra of the bulk, but there is a second uniqueness property in the volume of the state. The proof is quite complicated, but it is based on cluster property and a uniqueness theorem proved by Bernard K. I don't remember when. Okay, it's a classical theorem about uniqueness of quasi-free states. Okay, in all examined cases, it turns out also that if the state induced in the bulk exists, it is invariant under the killing symmetries of M or the restricted or a restricted killing symmetry group of the bulk I will examine later. Okay, also the Hadamard property holds for the state defined induced in the bulk, and a rough proof of this property can be obtained by using standard theorem of composition of wavefront sets obtained by Armander, noticing that the two-point function, these two-point functions, actually not this one, but the two-point function of the state induced in the bulk can be constructed by composition of three distributions. This one defined on the boundary and two causal propagators defined in the bulk with one of the argument restricted to the boundary. The causal propagator is the difference of the advanced and retarded fundamental solution. Okay, if one can use those theorems of composition of wavefront sets, it arises that the wavefront set of the state induced, the two-point function of the state induced in the bulk, has exactly the Hadamard form. In other words, it satisfies the micro-local spectrum condition. However, it holds provided those compositions can be constructed effectively. And this is not obvious because due to the singular support of the causal propagator, which could be singular, too singular, about the tip of the cone. So in general, the tip of the cone, I mean, look at this figure here. So in general, one has to check the behavior of the singular support, actually, of the wavefront set of this object near the tip of the cone. Okay, let's examine the first case I will consider in this talk. This is the case of the class of spacetimes which are asymptotically flat at null infinity, future null infinity. A spacetime with this shape is, roughly speaking, a solution of vacuum Einstein equations about the boundary, at least, which tends to Minkowski space-time approaching the null infinity. This is a very rough definition. Rigorous definition is, for instance, contained in Wall textbook. And the boundary, in this case, essentially by definition, has this form, which is exactly that we need for use our theorems. Here there is a more precise definition, but I don't want to stick to this definition. I only notice that the metric with the form we need is not the metric of the physical space, but is the metric of the unphysical space-time, which contains the physical space, and the boundary is a boundary, a true boundary in the larger unphysical space-time. This form of the metric is the form of the unphysical metric. One has to rescale the physical metric using this factor which vanishes exactly on the boundary. Okay, the unphysical space-time which is necessary to give the previous definition is not completely determined by the physical, by the physical space. As a consequence, the geometry of the boundary is not completely fixed, and a group of diffeomorphisms arises which describes such ambiguity. This is the group found by Bondi, Metzner, and Sachs, the BMS group, the famous BMS group, which is topologically, takes this form topologically, is an infinite dimensional Lie group. But the important property of this group, obtained in several steps by Giroch, Ashtekar, and Xanthopoulos, is that for a given bulk, which is asymptotically flat at null infinity, there is the homomorphism, injective homomorphism from the group of isometries, the killing isometries of the bulk, into the group, the BMS group. This injective homomorphism is obtained in practice extending the killing vectors of M up to the boundary, rescaling in some sense. In this case, we consider, for the algebra of the bulk, the algebra associated with a massless conformally coupled field. And in this case, the projection of the field on the boundary is constructed using this factor, which diverges exactly on the horizon, on the boundary, but the boundary is at infinity. The field vanish at infinity, and this product is finite, turns out to be finite. In this way, the projection map, when exists, providing several conditions about the behavior of the solutions, the restriction of the solution to the boundary are satisfied. The problem is what happens about the tip of the cone once again. In this case, if the behavior is okay, the symplectic form is preserved. The problem now is to find sufficient condition for globally hyperbolic asymptotically flat spacetimes, which are enough to define the state on the boundary. This is equivalent to to fix the behavior of the solutions, the restriction of the solutions about E+. Because this corresponds to give a precise definition of the symplectic space of the boundary, which must contain all the restrictions obtained by all wave function of all possible bulks. Okay, allora, sorry, I'm a bit tired. Those conditions, sufficient conditions, are the following, for instance, but I don't think they are necessary. If we restrict to the case of globally hyperbolic asymptotically flat spacetime, which admits future time-like future null infinity, and this means simply, no, not simply, but roughly speaking, that this is a true point in an extended manifold. This object is a point, and the structure about this point is just the structure of a null cone in, for instance, in Minkowski spacetime. In this case, the behavior of the restrictions of the wave functions about E+ is so good that all conditions are verified and everything can be proved. In particular, the embedding of algebras exists. The state for every bulk can be the induced state from the universal state defined on the bulk can be induced in any bulk with this property. This state induced in the bulk is invariant under every isometry, killing isometry of the bulk, if any. It has positive energy with respect to any time-like killing vector of the bulk, is Hadamard. And in case the bulk coincides with Minkowski spacetime, omega m coincides just with the Minkowski vacuum. Just a comment about the Hadamard property. The Hadamard property in this case is proved following the composition of wavefront sets. But after I obtained this proof, a referee of CMP pointed out to me that a similar proof was contained in the PhD thesis of Stefan Hollens in a completely different context. Okay, let's pass to the second class of spacetimes where our machinery works. This is a class of models of expanding universe. In practice, they are spacetimes which are perturbations of the Sitter spacetime in some sense. But in general, homogeneity and isotropy are not necessary in this case. Roughly speaking, we have to consider a class of spacetimes which admit conformal killing vectors, which becomes null-like about a three-dimensional null surface and becomes tangent to this surface. This is nothing but a past cosmological horizon. The integral lines of this vector can be considered as the world lines of galaxies in this model, and the surfaces, the three surfaces orthogonal to this vector, can be considered as the rest frame of the comoving frame with the galaxies. In this case, we also assume that the metric exactly on the past cosmological horizon takes this form in order to apply our machinery. There is also in this case, sorry, just a moment, I forgot no, okay. Also in this case there is a distinguished group of isometries of the boundary which takes this form. The action is quite complicated. This group is universal, and it has the property that it exists an injective homomorphism of groups which maps the symmetries, the killing symmetries of any bulk attached to the boundary into the group. In this case, the killing symmetries we consider are only those which become tangent to the boundary, approaching there. In this case, we can consider in general a general Klein-Gordon field, which every possible coupling with the curvature and every value of the mass differently from the other case. And also in this case, the problem is finding sufficient conditions for the existence of the embedding function of the algebras from the bulk to the boundary, and sufficient conditions for the existence of the induced state. Sufficient hypotheses are that the bulk spacetimes belong to a certain class of suitable globally hyperbolic Friedmann-Robinson spacetimes which are perturbation of the Sitter spacetime. I will not enter into details, but it's a quite large class of spacetimes, and describing inflection, for instance, in particular, for instance. Okay, in this case, once again, it happens that the embedding is well defined. The state induced in every bulk is invariant under the group of isometries of the bulk, but only the isometries which are tangent to the boundary. The state induced in the bulk has positive energy with respect to the conformal killing time, that defining, no, sorry, I'm not very clever with these. Allora, ecco, with respect to this killing vector. Okay, this state is Hadamard once again, and when the bulk is just the Sitter spacetime, the induced state coincides with the well-known Bunch-Davies vacuum. Actually, the bulk in this case is not the complete de Sitter spacetime only an expanding region of the zeta spacetime. I'm not very familiar with this point, but my colleagues are. They told me that the properties of the two-point function of this state as the property as such that it can be used in cosmology to model the scalar fluctuations of the cosmic background radiation. Ask them anyway. Okay, in this case, the Hadamard property cannot be proved by adding the tip of the cone, because the structure is too singular in the presence of a positive mass. It appears an divergent potential about the tip of the cone in this case, but it can be proved using an approximation of the two-point function by means a sequence of distributions with respect to the Hermander topology, and using the fact that those distributions have a suitable wavefront set. It's a continuity property of wavefront set used in this case. Well, the other case I will consider is this one. In this case, the space-time, the relevant space-time, is the union of the Schwarzschild wedge, the event horizon, and the black hole region. The boundary is made of two parts in this case, the past horizon and the past null infinity. So we have two parts for the boundary. In both cases, the metric takes the correct expression. The symplectic space of the boundary is a direct sum of the two symplectic space on each part of the boundary. The state, the universal state defined in the boundary, is the tensor product of the states defined on the two different parts of the boundary. To use our machinery, it's necessary that the symplectic space on the boundary contains the restrictions of the wave functions, the solution of Klein-Gordon equation of the bulk. And this is not a trivial task to give such a definition, but it was possible due to this recent work by Dafermos and Rodniansky, where precise estimate of the fall-off behavior of the restrictions of the wave functions, solutions of Klein-Gordon equations, a restriction to the boundary are given. It's given a precise estimate, so we can define very precisely the symplectic space. But these extensions is not simple, is not straightforward, because apparently, using the estimate by Dafermos and Rodniansky, it seems that the fall-off behavior of those restrictions is too slow. So the extension procedure was very complicated and involved several steps with in practice we decomposed each function in several parts and obtained an extension for each part and defined the final extension summing the results, and we had to prove that the final extension doesn't depend on the decomposition used to the decomposition used for the restriction to the boundary of the wave functions. Okay, anyway, using the results by De Fermus and Rodzianski, it's possible to construct this embedding, and it turns out that the state induced, well, now one can define immediately the state on the boundary. The state induced in the bulk is invariant under all Killing symmetries of the bulk, as before. This state turns out everywhere Hadamard. In the static region, on the event horizon, and in the black hole region, the proof is quite involved and relies on some properties of passive states concerning the region, the Schwarzschild propagation of singularities by front sets. Using a result by Fredenhagen and Haag, it's possible to prove that this state describes Hawking radiation about the future null infinity, because this state is Hadamard around the event horizon. This is a general result by Haag and Fredenhagen. Okay, the procedure used to define the induced state and the property of the appearance of the Hawking radiation at infinity is completely in agreement with the ideas of Unruh about the definition of a suitable state which describe Hawking radiation in a realistic collapse of spherically symmetric matter. This state is called the Unruh state. So in practice, we think that our state, this state, is the Unruh state, in fact. There is another definition of this state given by Dimock and Kay, but given only in the Schwarzschild wedge, and using an interesting technique based on the asymmetric machinery. But up to now, we were not able to prove that those states coincide. It's an open issue. It's possible to extend this state to the whole Kruskal manifold, adding this part of the boundary, using this boundary, but we don't expect that the obtained state is Hadamard on the whole Kruskal manifold due to the theorem of Kay evolved about the uniqueness of Hadamard states which are invariant under Killing isometries, because in this case the state should coincide with the Hartle-Hawking state, which is completely different from this state. Okay, let's pass to the last case. Just a moment, I have to. Okay, this last case is very elementary, but however is interesting. Let's consider a simple diamond in four-dimensional Minkowski space-time and consider a double cone in practice, and consider in this situation a Klein-Gordon field with strictly positive mass. The state, we are fix a state in Minkowski space-time which is nothing but the standard Minkowski vacuum, and consider this GNS triple. Restricting the GNS representation to the diamond. So we are in fact considering the algebra of the diamond in the GNS representation of Minkowski vacuum. The associated von Neumann algebra is the restriction of Minkowski vacuum is cyclic and separating for this, the von Neumann algebra generated by the GNS representation of the diamond. So there is a modular group, but up to now no explicit representation exists for the modular group. In case of vanishing mass, there is an important result by Hislop and Longo, which uses conformal techniques and reduces to the Rindler wedge by means of a conformal transformation. But in case of strictly positive mass, the problem is open. There is anyway a result by Figliolini and Guido, who obtained an indirect representation of the generator of the modular group in terms of the generator of the massless modular group, even for more general regions than the diamond, our diamond. Okay, in this case, we may apply our machinery defining the state on the boundary, which is completely independent on the mass. By construction, the embedding of algebras exists in this case. Is straightforward to prove that the existence of this embedding. It's possible to define the induced state in the bulk, and it turns out that the induced state in the bulk coincide just with the Minkowski vacuum restricted to the diamond. But this is not the only interesting result, because it turns out that the von Neumann algebras associated with the GNS representation of the restriction of the the GNS representation of the diamond, yes, this one, and the von Neumann algebra constructed on the boundary with respect to the universal state are unitary equivalent by means of a unitary which implements this embedding. This is not trivial because this is not surjective. So these results holds only at level of von Neumann algebras. Okay, in this case, we can construct the modular operator of the bulk in terms of the modular operator of the boundary, using the unitary intertwiner, which contains all the information about the mass by construction. The mass must enter only this object. There is no other place where the mass can enter. Okay, the point is that this modular operator doesn't depend on the mass, because it's completely constructed in this von Neumann algebra, which is defined with respect to a state which doesn't know the value of the mass. Okay, so we have to study the modular operator of the theory of the boundary, and it turns out that it has an geometric interpretation. In fact, it is just the group which implements the one parameter group generated by this vector field defined on the boundary. In practice, this vector field is that found by Hislop and Longo, projected on the boundary, where the mass in some sense vanish, in some sense. So we have another indirect geometric representation of the modular group of the massive theory in a diamond. All information about the mass is contained in the unitary. The next step, which is still work in progress, is give an explicit representation of the self-adjoint generator of the modular group in the bulk using the explicit expression of this unitary operator. The problem is quite complicated, technically complicated, because one faces the Groussard problem, the characteristic Cauchy problem, which is not so simple to handle. Okay, I can pass to the conclusions. The most important open issue concerns the fact that we considered only the non-interacting case. So we want in the next future to try to extend our result at least to Wick polynomials. I mean, we want to try, we will try to extend this embedding. It's in fact a star homomorphism of injective star homomorphism of C-star algebra. In some sense, we wish to extend this object to Wick polynomials of the field, at least to encompass interaction at perturbative level, at least. Another important issue is to investigate the Unruh state, the existence of the Unruh state, the definition of the Unruh state by means of our machinery in the case of a massive field. The basic problem is that we have no estimate for the fall-off behavior of the restrictions of wave function on the boundary in this case. So it's not very simple, is it impossible at the moment to define a symplectic space on the boundary. Next, an important issue is to extend our machinery to give a proof of existence of the Hartree-Loking state in the whole Kruskal manifold. This is quite complicated because it seems that the fall-off behavior of the restrictions of the wave functions on the future infinity is not appropriate for a KMS state, for a two-point function of a KMS state, but perhaps it only means that the Hartree-Loking state cannot be defined using our approach, and nothing further. Okay, that's all.
Thank you very much, the speaker, for this interesting lecture. And are there now some questions or comments? Yes.
Would you also expect spinor fields to fit into this framework?
Yes, I expect that the machinery can be extended to that case, and in this case, perhaps things are more simple, because concerning, for instance, the Groussard problem, there is a result about the several interesting properties for our procedures, which are valid only for the spinorial case, but not for the scalar case. So it could be possible to control the behavior of the restrictions of the wave functions about E plus automatically without any complicated procedure.
Yes.
Similar question. What about the electromagnetic field?
No, I don't know. I don't know.
It is known that the generator in some models of the modular group
Yes.
is the boost operator.
Is it?
Of the Lorentz group.
Yes.
Now you can restrict the boost operator to
No, it's not the boost operator. No, it's a pseudo-differential operator, I think. It's much more complicated. It's not a standard differential operator. I have a form, but I cannot write now because it's a work in progress. But it's completely different. It's not the restriction of the boost.
Any other questions or comments? I had a question.
Yes.
Is, for example, the investigation concerning anti-de Sitter space and theories of the boundary related can be envisaged from this type of methods?
No, in my opinion, my honest opinion, this approach has nothing to do with the conjecture. Yes, in my opinion. At least up to now, perhaps including interaction, the picture could be changed completely. Because in that case, interactions, as far as I know, are very important. So I don't know. Also, in that case, the boundary is time-like and not null-like. So our machinery cannot be applied. There is no symplectic form which is preserved in some sense.
Thank you. No other questions? So we thank again Mr. Moretti. According to the tradition as the last chairman of the conference, and will add 2 words, very short, conclusion concerning this conference. I think it has been a very great pleasure for me, and as far as I heard from all people, to have this big conference, which was a success on 3 points. First of all, by the high quality of all the conferences, by the number of participants interested in this conference, and by the quality of the organization also. And these in these three aspects, one has to stress the interference, active interference between old generation and young generation. That's fantastic to see all this young generation interested by this subject, and how in this subject, which is not the case maybe of all subject of research, there has been a very wide transmission of knowledge throughout the generations. And I think this leads us to thank at all levels the organizers. First of all, I begin by the young organizers, Dorothea Van and Pierre Martinetti, but also I have to thank especially, I think, for his enormous work of organization, Karl-Henning Reven, on which the very hard aspect of all this organization has been taken in charge. And of course, the immense pedagogical work which is behind which is, and then it leads me to quote in particular, to quote, of course, the pedagogical work and talent of Detlef Buchholz. And I think really this achievement of this conference is for him a magnificent celebration for his 65 years, for all his career of professor. And so I can now express in a twofold way my wishes, best wishes to the quantum field theory, algebraic quantum field theory, with its opening to all of techniques, and best wishes also for the future career of researcher, of pure career of researcher of Detlef Buchholz now. And so I hope that in the next future we'll have again such wonderful conference.
I want to thank especially the speakers for their excellent talks and interesting talks. I want also to thank the audience for their interest and participation through questions and discussions. Like you mentioned, the transfer of knowledge between generations. I think this is a transfer in both directions. That's probably what you meant. Yes. It's not, I think the young people active in this field really produce interesting new insights, and which the people from the old generation may not have dreamt of. And so this is, I can just agree to what you said. It's this transfer between the generations is maybe the most interesting or most promising aspect of what we have seen here. So thank you very much again to everybody, and I wish all of you a good way home or to Prague or to other places, wherever you go, and we shall see each other again in some place of this world. Thank you very much.